This lesson is going to go through 4.3, the derivatives of inverse trigonometric functions. We are actually going to go through the derivatives of regular inverse functions as well, and that's actually the first theorem that I have here, and the corresponding example is going to go along with that. So there is a graph in your book on page 173, so I do want you to read over that and look at the graph. It deals with why this theorem is what it is. So if you have a point AB on your graph, and if you look at the slope of the original function at A, and if you look at the slope of the inverse function at B, because you know the inverse function would be the point BA instead of AB, they actually have this type of relationship. So they're actually reciprocals. So that's where this formula comes from. So this is the inverse function slope relationship. So if you have some inverse function of your original function at A, keeping in mind that if we say that the inverse of A is the inverse at A is equal to B, that means if we take the derivative of that inverse at A, that's going to be the same as 1 over whatever the derivative was at that B value. So that's what we're going to be using this formula in the very first example. Okay, so we have here, and I know the view might be a little bit off because this was snipped from an old AP test, and I have seen these appear on a lot of different tests, especially if there is going to be a multiple choice section this year, like there has been in most of the years in the past. So we know that f of x is equal to 2x plus 1, the quantity cubed. G is going to be the inverse of f. And we are given that f of 0 is equal to 1. We want to know what is the value of the derivative of g at 1. Well, a couple things to note here. Because we know that g is the inverse of f. If f of 0 is equal to 1, that means that g of 1 is equal to 0. So we have that relationship. So if I were to take the derivative of this, notice that's what they're asking us to find. They're asking us to find g prime at 1. That means that according to the previous formula, because g is really f prime, g prime at 1 is going to be equal to 1 over f prime at 0. Again, because g of 1 is equal to 0. So that's where that relationship comes in. So to do that, we have to go through and find f prime. So I have my original function here, 2x plus 1 quantity cubed, using the chain rule. That's going to be 3 times 2x plus 1 squared times the derivative of the inside, which is 2. So that's going to be 6 times 2x plus 1 squared. And we are evaluating this at 0. Because again, I want to find f prime at 0, and my g prime at 1 is going to be the reciprocal of that. So this is going to be 6 times 2 times 0 plus 1 squared. Well, 2 times 0 is 0, plus 1 is 1. 1 squared is still 1. So this is actually equal to 6, which means my g prime at 1 is equal to 1 over 6. So D would be my correct answer there. And that's how you utilize that formula to find the derivative of some type of inverse function. I don't expect this to be a huge part of the exam, but you could almost plan definitely on it being at least one of the multiple choices. This is a formula you'll have to memorize. It's not something they're going to give you. Okay, so now that brings us to the actual trig derivative part here, which is the main reason why we're going through and doing this lesson. So we're trying to find the derivative of arc sine, which is the inverse sine. And so we're given here that y is equal to the inverse sine of x. Well, if we rewrite this, this means that sine of y is equal to x. Because we would solve for y by doing the inverse sine of both sides. That's how we got that inverse sine there. And so if we go through and take the derivative of both sides, so d dx there, d dx there, I end up with cosine of y times dy dx is equal to 1. And so if I solve for my dy dx, I end up with 1 over cosine of y. Now, that probably doesn't look like something that is very nice, something that you're going to be able to work with very much. If we go through and think about your cosine of y, if you recall, we have this relationship. The sine squared of y plus cosine squared of y is equal to 1. So I'm actually going to solve this and rewrite it so that I can find something in terms of x to put in for this cosine of y. Also, because we are dealing with inverse sine, if you recall, x is going to have to be in between -1 and 1, and it can't be equal to -1 and 1 because that is not part of our domain. And this is on -pi/2 to pi/2. So just something to keep in mind whenever we're going through this. So cosine squared y is equal to 1 minus sine squared y, and I take the square root. So my cosine of y is equal to the square root of 1 minus sine squared y. Well, according to my original equation over here, before I actually took the derivative, sine of y is equal to x. So this is actually the same thing as the square root of 1 minus x squared. And that's where we get our formula here. So since cosine of y is equal to the square root of 1 minus x squared, that means that my dy dx here is equal to 1 over the square root of 1 minus x squared. Now, you may be thinking up here, well, why didn't we put plus or minus? Because we took the square root of both sides. And that has to do with our bounds here on the function. So that's one of the reasons why we didn't use that. But this is actually your formula here. Your dy dx is going to be equal to 1 over the square root of 1 minus x squared. And then normally you would have to multiply by the derivative of whatever your x value is. And that's what we have on the next page. So you can see up at the top, I replaced my x's with the u's, but I did also multiply by this du dx. The only condition here is that if you take the absolute value of u, it does have to be less than 1. So again, it's going to be something in between -1 and 1 because those were the restrictions on x, just like they were whenever we did that previous exploration. That's actually the only inverse function derivative that we're going to derive. The rest of them I'm just going to give you. The inverse trig functions, you will have to memorize them. Just like with a lot of other these nitpicky things, it's not something you're going to have to use a ton, but you will have to memorize them and use them where appropriate. So now we have example 1, where we're going to find the derivative of the inverse sine of x squared. So in this case, my u is x squared. So the derivative is equal to 1 over the square root of 1 minus x squared squared, and that will become x to the 4th. And then I'm going to multiply that by the derivative of that u. So I'm going to multiply that by 2x. So my final answer would be 2x over the square root of 1 minus x to the 4th. And there's our solution. So easy, plug into the formula. Page 175 actually goes through the derivative of arctangent. So the inverse tangent of some u, this one's actually the simplest formula out of all of them. It's 1 over 1 plus u squared and then times the derivative of u. Tangent is actually the only one that doesn't have a square root in the solution. So it's typically going to be a little bit easier to work with than some of the others. And again, you do still have to multiply by that derivative of whatever your u is. And again, that's because of the chain rule. Okay, so we have, for this example 2, particle moves along the x-axis. Its position at any time t is greater than 0 is given below. So this x of t is equal to inverse tangent of the square root of t. What is the velocity of the particle when t is equal to 16? Well, velocity, if you recall, is the first derivative. So I'm going to be taking the derivative of this inverse tangent. Also note this square root of t, whenever you're finding the derivative of that value, you want to think of it as t to the 1/2 power. That's going to be a little bit easier to take the derivative. So we have 1 over 1 plus, this one also has a plus instead of a minus, the square root of t squared times the derivative of the square root of t. Well, the derivative of the square root of t is 1/2 t to the negative 1/2 power. So if we go through and clean that up a little bit, the 1/2, the 2 is actually going to be on the bottom. This t to the negative 1/2, that's going to be on the bottom. So I have 1 over 2 square root of t times 1 plus t, because this square root of t squared, that's actually going to end up with just as a 1 plus t. And so I'm going to evaluate this at t equals 16, like it tells me in the question. So I have 1 over 2 times the square root of 16 times 1 plus 16. So square root of 16 is 4. 4 times 2 is 8. So it's 1 over 8 times 1 over 17, which is 1 over 136. That doesn't give me any units here. So it would be units per unit of time, but it doesn't give you anything like that. You can just leave your answers 1 over 136. Please make sure you are looking though, because if it did give you units and this was an AP free response question, you would have to give the units in order to get full credit. Okay, last formula. And I know this is only the third inverse trig formula, but I'll explain why it's the last formula in another slide. This is inverse secant. So secant, this one is kind of complicated just because it has more parts to it. So it's still 1 over. Notice you have the absolute value of u on the bottom. So whatever your u equation is, or your u wouldn't really be degree, it would be value. And then that's times the square root of u squared minus 1. Notice this one is not like sine. Sine is 1 minus u squared. This is u squared minus 1. And then again, I'm multiplying by the derivative of u. For this one, the absolute value of u has to be greater than 1. And this is because secant can't be anything in between negative 1 and 1, normally. So here, we're taking the derivative of inverse secant, and this is just straight up using the formula. Your u is going to be 5x to the 4th, just something to keep in mind. So I have 1 over the absolute value of 5x to the 4th times the square root. And I'm actually going to make that not a parenthesis. I'm just going to do my square root there because that'll act kind of as a grouping symbol. So my square root of 5x to the 4th squared minus 1 times the derivative of 5x to the 4th, which is 20x to the 3rd. So going through and simplifying this a little bit, I'm going to have 20x to the 3rd all over this absolute value of 5x to the 4th. I can actually get rid of the absolute value. 5 is already positive. X to the 4th has to be a positive number because it can't be imaginary, so it's an even exponent. So I can just make that 5x to the 4th, and then I have my square root, and this will be 25x to the 8th minus 1. Make sure you square both the coefficient and the variable, and now we can go through and reduce. So the x to the 3rd can take out all but 1 of the x's on the bottom. The 20 becomes a 4. The 5 is gone. So this is equal to 4 over x times the square root of 25x to the 8th minus 1. Okay, and there's your derivative of inverse secant. Now, there are 3 trig functions we didn't talk about. Cosine, cotangent, cosecant. Well, what do all those have in common? They're all cofunctions. And if you recall, back when we were learning about the derivatives of the cofunctions, they were all negative. And that's basically all you're going to do for the derivative of the cofunctions when they are inverses. So normally you would just take your pi over 2 and subtract out the corresponding regular function. But because of those results, here highlighted in yellow, your derivatives are just the negative of the corresponding function. So to find the derivative of the inverse cosine function, you're going to do the inverse sine function, and you're going to make it negative. So instead of 1 over, it's going to be negative 1 over. And the same for cotangent, the same for cosecant. So you really only have to memorize the 3 formulas for inverse sine, inverse tangent, inverse secant. And then remember, if you're finding the cofunction derivative, you just put a negative in front of it. And that brings us to example 4. Find an equation for the line tangent to the graph of y equals inverse cotangent of x at x equals negative 1. So we do have to find, since we're finding a tangent line, we do have to plug in that negative 1 in order to find the value. And we can actually use that relationship to find this out. So if I'm finding the cotangent of negative 1, that's pi minus the inverse tangent at negative 1. Well, remember that we're bound in between, for tangent, I think we're bound between pi over 2 and 3 pi over 2, or 0, I think it's 0 and pi. 0 and pi is where we're bound for tangent. So this is going to be pi over 2 minus, and tangent, or I'm sorry, inverse tangent it's on the same bounds. It's negative pi over 2 to pi over 2. Tangent is a negative 1 whenever we're at negative pi over 4. So the inverse tangent would be equal to negative pi over 4. So pi over 2 minus negative pi over 4 is going to be 3 pi over 4. So that's actually going to complete our ordered pair there. I do suggest you look back over the inverse tangent values, because you basically have to think through the regular value and then kind of switch it up a little bit. So now we have to find the derivative. This is a cofunction, so it's going to be negative 1 over 1 plus x squared, and using the chain rule, I would just multiply by 1 because the derivative of x is just 1. And I'm evaluating that at x equals negative 1. So this is negative 1 over 1 plus 1, which is 2. So negative 1/2 is going to be my slope. So my tangent line is y equals negative 1/2 times x minus negative 1, so plus 1, and then plus 3 pi over, I realize here I wrote 3 pi over 3. That should be 3 pi over 4. So plus 3 pi over 4. And you can leave your answer like that. There's no need to simplify and go any further. So look back over these. I know that the inverse trig functions are not something we spend a whole lot of time on. I'm sure that there are some Excel sections on them if you need to go back and practice any of those skills. There's also the book video. The book video may go into a little bit of a deeper explanation than whatever I did. You have a homework assignment that is due on Wednesday. So work through this. We do have office hours coming up, so feel free to pop in, ask me any questions that you guys have.